Okay, so the good news is that Steve was not even bruised because of his rubberized suit. In fact, what happened was he struck the ground and rebounded straight back up into the air with an initial velocity of 80 feet per second. So my next question is, how high did Steve fly to the air on the rebound? So what we're going to do is set time equals 0 to when he hits the ground at that 5.906 seconds. That's going to be our new time equals 0. So the initial velocity that we're given, v of 0, equals 80 feet per second. So the position function now, s of t, is going to be that negative 16t squared. And this comes, of course, from integrating acceleration to velocity. And let me give you that velocity equation, because when I integrate acceleration of negative 32, it goes to negative 32t, but the initial velocity was 80. So when I integrate this velocity equation, I get negative 16t squared plus 80t plus initial position, which we're going to say is 0 because he's on the ground. So now we want to know how high he flew into the air. Well, so he hits the ground and he goes back up into the air, and then of course he's going to eventually come back down. So at this moment when he hits the highest point that he's going to hit when he goes back into the air, that derivative must be 0. So we can set the velocity function equal to 0 to find out what time has gone by when Steve reaches his maximum height. And this time is going to be 2.5 seconds. So really what I want to do is plug 2.5 into my S equation to find out just how high Steve went on his rebound. And I'm going to use my calculator to evaluate all of this. And I find out that S of 2.5 is exactly 100 feet. So that's how high Steve went on the first rebound. Okay, so Steve kind of bounced up and down for a little while, and then he slowed down enough that he knew he had to make a getaway because the police were swarming the scene. And he knew he could outrace them if he could just get to shouldn't say my friends, it should say my amazing Audi Q5. There's some typos in here, so remember that we're in my Q5 here. Okay, not to aid and abet a criminal, but I did throw Steve the keys to the car. Okay, so now he went from 0 to 60 miles an hour in 4 seconds, and we're assuming constant acceleration. So this time he's not leaving the ground, so gravity is not acceleration anymore. We can actually calculate acceleration using just this information. Acceleration is going to be the rate of change of velocity, and they're telling us it's constant. So all I have to do is take the average rate of change from 0 to 60 over the time period 0 to 4. So I'm finding out that my acceleration is going to be 15 miles per hour per second. So that's a kind of a complicated units situation. So instead of dealing with miles per hour per second, what I'm going to do is do a dimensional analysis here. So I have miles per hour times second in the denominator. And then I really want this to be in either feet per second or miles per hour, but I think feet per second will be easier for me to understand exactly how far Steve went. So what I'm going to do is say 1 hour up here divided by 3,600 seconds, because 1 hour is 3,600 seconds, and then 5,280 feet divided by 1 mile. And then my miles will cancel here, and my hours will cancel here. So when I work this out, I'm going exactly 22 feet per second squared. Okay, so that is my average acceleration. I need to integrate acceleration to get to velocity, and of course I do that using the power rule. So velocity is going to be 22t, and they told me my initial velocity is 0, so my plus c here is 0. And then of course I integrate v to get to position. So when I go up a degree and divide by the new degree, I get the position equals 11t squared, and I'm assuming of course he starts at ground 0. And then moves. And so the real question is, how far does he go in 4 seconds? You just have to find S of 4, which is 11 times 16, or 176 feet. Now, the good news is that Steve moved in a perfectly straight line from the Washington Monument across Constitution Avenue and crashed into the Smithsonian, but he was okay because the fluffy woolly mammoth got the brunt of the impact. Before the crash, in a span of 30 seconds, Steve covered 5,000 feet. One of my former students was a police officer and added speeding at over 100 miles per hour to the charges using the facts above. Show how this can be proved. Well, he covered 5,000 feet in 30 seconds, sorry. So that's feet per second, which means his average velocity was 5,000 divided by 30 feet per second. Well, how can we determine that that is 100 miles an hour? We can do another dimensional analysis. So what we're going to do is put in 3,600 seconds again, divided by 1 hour. And then for feet, I'll have 1 mile up here and 5,280 feet. And of course, my feet now cancel and my seconds cancel. And I'm going to be left with just miles per hour. And in units, or when I simplify everything, I get 113.636 miles per hour. Now, that doesn't tell me that he for sure went 113.636 miles per hour, or does it? What theorem do you know that can guarantee the existence of an instantaneous rate of change equal to this average rate of change at some point on an interval? That, my friends, is the mean value theorem, which you also learned back in Unit 3 when we were discussing the application of derivatives. So the mean value theorem states that if I have a closed function on the interval, a continuous function, on the closed interval from 0 to 30 seconds, which we do because he moved in a straight line, unfettered, and if it's differentiable on the open interval, 0 to 30 seconds. So I'm writing this out, but I need to state continuous on the closed interval, differentiable on the open interval. I must state that these two conditions are met. And once those two are met, then the mean value theorem applies, which means that by the MVT, the instantaneous rate of change will have to equal, instantaneous velocity equals 113.636 miles per hour at least once on the interval from 0 to 30 seconds, which of course is greater than 100 miles per hour. So my very savvy former calculus student, now police officer, knows the MVT and can use it to write a ticket.